We started talking about organic compounds and we looked at how to name them. And so this is going to be a big part of the rest of the class, is dealing with these organic compounds, naming them, drawing them, looking at different versions of them. That's what we're going to work on today. Tuesday, we'll be working on this more, and then in lab, we don't have too much to do. We're just going to be checking out of the drawers. So we'll spend the rest of the lab time, or as much as we need, finishing this up, and then we'll have our last quiz on Thursday, the last day of class, which will be on this, on this chapter 11. Then remember the final exam is going to be on the Tuesday of exam week. I don't remember the time. Anybody write that down?
It's like
1:45 or something. I think 1:45. Okay. So we'll do that. Okay. Now we talked about drawing these structures in a couple ways, in condensed forms or in full out forms like that, these alkanes. We looked a little bit at isomers, different ways to draw the compounds, and we talked about how one of the difficult things about isomers is actually figuring out whether or not they're the same. Because sometimes if you kind of draw them all twisted up, they look a lot different, but actually it's just a different way to draw the same compound. So then we looked at names, and the names are actually a really nice way to determine whether or not you have an isomer, because if two things are isomers, they'll have the same formula, but they'll have different names because they'll be connected in different ways to the different molecules. If they have the same name, then they're not isomers, they're just the same. They're the same molecules. So we're going to practice that a bit today and look at some different possible ways of drawing that. So I want, grab some paper, and which hopefully you have anyway. And we're going to draw isomers of hexane. So that is structures with formula C6H14. So 6 carbons, 14 hydrogens. One of them is this simple straight chain. Looks like this. But as we looked at last time, there are lots of other ways that we can draw 6 carbons kind of branched off from each other. We can disconnect them and put them together in different ways. So see if you can draw as many different isomers as you can that still have 6 carbons and 14 hydrogens. Remember, one of the ways we said helps with this is to take all the hydrogens off and just think about the carbon skeleton and how the carbons are connected. And when you think you've got one that's different from this one, come and put it up on the board over here, and then we'll talk about how to name them. Nothing yet? Gotta have one. Nobody? All right, keep thinking.
Yeah. You just care about the carbon?
Yep, we can just do the carbons for now. Actually, put the hydrogens on them too, but start with the carbons. Everybody? Thanks. Anybody find any more? Thanks.
Be just careful.
Just a straight line.
Let's try it for two more, and then we'll start talking about it. Yep. Go ahead. That's all right.
And then your name, you're going to do kind of do it on. Yeah. Because this is how you guys see it now. This is the This is the setup for this right here. Oops. Did I miss it?
Don't worry. It's okay.
All right.
Alright. You can see it here.
Yeah.
Probably I'm wrong.
Well, that's good. Let's start. So let's start with the blue one here. What is the what are the naming rules? Should we put them back up here? We got to find the longest continuous carbon chain first. So what's the longest continuous carbon chain in this blue structure? 6. Kind of the entire thing, right? They all connect to each other. So then how do we name this?
Wait, it's gonna be the same thing as the one we had, the first one.
Right. So this is actually the same as just all of these written in a row. Which would be what? What's the name of that? That's hexane. So 6 carbons in a row that are connected to each other, no matter how you write them, is always going to be hexane, even if it twists around or makes a snakes or whatever.
How are you getting 3 connected to each other in that little grouping at the end? Where's the 3 carbons going? I mean, if it was just
2, 3, 4, 5, 6. So 6 carbons in a chain.
no, I mean, but I'm sorry, the hydrogens.
The
How
hydrogens?
are 3 connecting on the end of that one if it's connected to the other
It's not
carbon?
connecting it.
It's not.
Well, I think what the idea is when you draw these condensed structures, even if the line doesn't directly go to the C, you assume that the hydrogens are on the carbon, are attached to the carbon. Just like these tell you there's 2 hydrogens coming out of this carbon. So this would be, so even though this clearly looks very, very different from our other structure out there, when we analyze it by looking at the longest chain, we can see that it's actually the same thing. All right, so while we're over here, let's look at this one. What's the longest chain on this one here?
4,
Where do you see 4?
3 of them.
Like that, starting
Like
where?
a mouth.
Like an L.
No, it's not.
Go from one
Three.
end up and then to the right.
So 1, 2, 3,
It's
4.
like a sideways up.
One
Yeah.
more, go down one.
Yeah, that's right, because then we can go one more too, right?
But then you could go there.
Can you though?
No.
No.
It's the same one as the other one, now that I look at it.
Wait,
So
Oh, no.
that's actually the longest chain because we don't connect here.
Right, that's right.
So maybe let's write this as a condensed structure, maybe we can see that a little better. So
So
that
it's
would
5, not,
be CH2, CH, CH3, CH2, CH3, CH3.
oh,
Okay, so here's our chain. And what does that make this other thing?
penta.
Yeah, that makes this part a substituent. So not part of the main chain. So we found our chain, we found our substituents. Now we're going to number the carbons. So the substituent is closest to 1. Does it matter which side we start on here?
No.
It doesn't because that's right in the middle. So we'll start here, 1, 2, 3, 4, 5. 5 carbons gives us what name? Pentane. And so then what's the substituent here? Methyl, the 1 carbon substituent, so that's methyl.
Oh, wait.
3 months.
And since it's on carbon number 3, we need to specify that in the name as well. So this is 3-methylpentane. All right, so that tells us there's a methyl group on carbon number 3 of a 5 carbon chain, a pentane chain.
Wait, where did you get another from?
A 1 carbon substituent is called a methyl.
Oh, carbon outside here.
You can see that right up here in the. Okay, great. So that tells us that even though this has the same formula, still C6H14, this is a different compound from hexane. And it'll have different behavior. It'll have a different boiling point, different melting point. It might dissolve things differently.
What is the first number? Because I remember last time we had the 2 comma. What is the
Right.
other number?
If there are multiple substituents, then you need commas to separate the numbers of each
number's
one.
gonna be how many substituents or?
Right. Not where they are. So each substituent gets a number,
Okay.
and then depending on which carbon in the chain it's attached to. So let's look at, let's go all the way over here to this green one for an example of that. What's the longest chain over here on this green one?
4.
4? Which 4?
Cross?
you can start at the top or bottom, actually.
Yeah, you can actually start anywhere here, here, or here. We'll start here because it's nice to just go across. So there's our 4 carbons. We can't get any longer than that. And that means that we have 2 substituents, one here and one here. Okay, how are we going to number this chain then?
Starting with
Left to right, so that these go on number 2. If we started and went right to left, then these substituents would be on number 3. So that would be quite as good. And so what's a 4 carbon?
This methylbutane, isn't it?
Yeah, so this is going to be a butane because it's got 4 carbons. And what are the substituents?
There's two.
There's two of them, and they're each methyl. So that means that we're going to say dimethyl
Oh,
to indicate that there are two methyl substituents. And what carbons are they on?
three.
Two.
Two. They're both on carbon number 2. So each one gets its own number. 2,2-dimethyl-butene.
So first number tells you how many there are.
No, the prefix on here tells you how many there are. The di tells you how many there are. The numbers are where they are on the chain. All right, let's try this one. See if you can try this one on your own. Come up with the names of that structure here. And I'm going to copy these onto the notes. So, anybody come up with a name for this one yet? This is the one in red there. You think so? What do you think?
I got two methylpentane.
2-methylpentane. Anybody get something different? No? All right. So because you agree or because no one else has any idea?
I agree with that one.
Okay. Yeah.
But the other one only has 4, and that's butane.
Right. So this is saying that this has a chain of 5.
There's the one on the end.
Yeah, there's
Right.
5. There's one.
1, 2, 3, 4, 5. So yeah, that's the correct name there. And again, a different name, very similar to this one, but a different name. So we know those are different. There is one more isomer that we didn't get. So actually, it's pretty good. We got all but one. So the last one, I'm going to give you the name of it, and I want you to write the structure. Okay. The last one that you didn't get is 2,3-dimethylbutane. So see if you can draw a structure for that.
Oh yeah, that looks good. Put it on the top and down.
We got it? We want to come draw it?
Got it.
He's looking right at me. He's like, come on.
You seem so confident about this.
I'll go.
Okay, thank you. Come on up. It's just all an act, is that what you're saying?
Yeah, that's what it is. I just put on a front for you, Joe.
Okay.
It's just the same thing as the first one, you can make positions. So I'll just do.
Joe does that too, chicken. Yeah, I'd be upset next semester. Did you ever go on the rate mic with Bussy.com? Yeah. Yeah. You can see, like, I went down there because I had to write something, and there was a lot of negative comments, and I was so upset. I was like, why? Who can hate Joe?
Well, thanks for writing something nice.
No problem. You'll know it's me.
I put my name.
Okay, I'll have to go check it out now. All right, what do you think?
Yes.
Yeah?
Yeah.
I would say this is,
I put the C, I don't know why I left. Erase the,
what? How do you want to correct it?
since I moved it, then the H. I gotta erase the.
Oops. Because if they're together, then it doesn't. Is it, really, you could erase this with
Yeah.
this? Oh, cool. How do I, hold on. Okay, since I moved it, I'm gonna have to compensate for the 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. No, wait a minute. Yeah, it's 14, right? Hydrogens?
Yeah.
Okay. And if it's 14, then yeah, I think I was right. Why is that 2?
You need one more carbon.
Yeah.
Pop there, yeah.
Wait, I think I was right. So you switch positions because the first one, 2 means is on the second, and 3, the other one is on the third.
Right.
But I just want to make sure all the hydrogens add up. That's what I thought I was like 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, never mind. They're all 14 hydrogens, right? So it's all there.
It's there.
Oh, it's there. Okay. I don't know why I second guessed. All 14, right?
I think so.
All 14.
Oh, you have
All of them
Right.
are there. I
Alright,
thought I was
I'll-
missing a hydrogen.
Never mind.
So this is 2,3 dimethylbutane. Anybody see any issues with this, or this looks good? Yeah, it looks good, or yeah, you see issues?
I could be an issue.
Right, it's just the hydrogens and the carbons need a little correction. Remember, each carbon needs 4 bonds. So, and this is really easy to get confused of when you're dealing with these condensed structures. So that's why it can be helpful to write them out fully first and then condense it down. But what we see here, this all looks good, but this carbon, if it's a CH2, that means that it has 2 hydrogens plus this carbon plus this carbon. That's 5 bonds total. So that can't be right. So that must just be a CH. And then over here, this carbon needs 4 bonds
So you could add,
and needs an extra one, because if it's only CH2, that's 3 total bonds to that carbon, when actually it needs 4.
move it and add that,
So
right,
what
right.
about the second one, doesn't it need 4?
This one?
Yeah.
Yeah. So we've got 1, 2, 3, and then 1 more from the hydrogen. So that's 4.
So you just-
Because if we wrote this out, it would be like this.
Right, right.
Yeah.
Okay, okay. Yeah, that's right. So this is-
Right. So that's why it's helpful to use the carbon skeleton first. So only deal with the C's and then stick whatever hydrogens on you need later, so that you have enough, so that each carbon has 4 bonds. And we'll practice this more in the homework, of course.
With 3 dimethylbutane, we want to
Let's look at that. See if you can draw 3,3-dimethylbutane.
Just 3, 3.
Yep. So did you get something like this? Something like that?
Yeah.
So what's the
It's
problem?
gonna be 2 because you start with the closest to the end.
Right. So 3,3-dimethylbutane is actually the same as 2,2. It's just flipped over. You see that?
So, yeah.
Because if we were to actually go name this molecule, we would start counting over here and go 1, 2, 3, 4 to give us lower numbers. So that's why this one doesn't count as a separate isomer, because it's the same as 2,2.
Could you still name it 3-3 though? Or no, it just counted as the same, you just still name it 2-2?
It would be 2,2-dimethylbutane, right?
I have a weird question. What
Okay.
is our rule of knowing either have to go this way or this way?
Whichever way makes makes it so the substituents have the lowest numbers. So whatever side the substituents are closest to, that gets the 1. Right. All right, we don't have a lot of time, but let's throw some more in here. All right, a couple other things that you might encounter in these names. First, a group of molecules called cycloalkanes. What do you think that means? Like they're riding bikes?
They're in a circle.
They're in a circle, yeah. So these would be things that are connected together. So instead of, whereas hexane would be 6 carbons connected in a row,
Isn't it that one that the hexane kind of like a cycloalkane?
yeah. If they're all connected together in a ring, this is now known as cyclohexane. And notice it doesn't have the same formula as hexane, so it's not an isomer.
It's a totally different thing.
Right. Not an isomer of hexane. This is C6H12, whereas hexane is C6H14. If it goes around in a circle, you have to take 2 hydrogens out to get them to connect that way. So when we name cycloalkanes like these, the cyclo thing becomes the main name, and then you put the substituents on accordingly. So for example, a molecule like this, we would not say, oh, the longest chain is this, because we have this ring. So when you have the ring, the longest chain becomes the ring. And then these other things become the substituents. So we have a substituent here that's a methyl, and we have one here that's an ethyl, 2 carbons. And we start numbering around the ring. But of course, in a ring, you don't have an end to start at. So you can start anywhere. So you want to start wherever, same rule, wherever the substituents get the lowest numbers. In this case, we start down here and go 1, 2, 3, 4.
Could you do it the other way too?
Start here, you mean? You could. The technical rule with that is that you have to keep the substituents, you give them priority in alphabetical order. We're not going to worry about that. So yeah, for our purposes, either way would be okay.
And what is it to the side, H2? Is that what it's on?
These are two hydrogens connected to this carbon. Yeah. You can put them on either side of the carbon. So this name would be 1-ethyl 2-methyl cyclobutane. Because you're having such a good time? Is that-
It's just like,
That sounds intense.
All right, so but if you break, yeah, these names get kind of big and ridiculous, but if you break them down, they all end up using the same rules, following the same procedure as any small name. You've got your main structure, the main chain at the end, which could be a cyclo or it could be straight. And then you've got the substituents coming off, labeled with whatever carbon they're coming off. Speaking of confused looks.
Can you write that like a formula written without a name? What's the formula like? Do we just
You just count, yeah. So you'd count all the carbons and the hydrogen. So this would be C7H14.
and it doesn't have.
Yeah, there are going to be a lot of different possible structures that could be C7H14.
It's just not the same.
It's not the same as heptane, which would be say C7H16.
So when I see some of the products says methyl something, it says paraben next to it, and what's that? Like, you know, I know parabens.
Paraben refers to a particular type of structure. I think it has to do with waxes.
Oh.
Oil, it's a type of an oil or a wax. I don't know for sure what that structure is, but we can look it up. One other thing you'll encounter in these names oh, well, I guess something else generally we should say about the names before we go on. That brings up a good point. If you look at various ingredients of products like foods and cosmetics and things, you'll see a lot of names that sort of look like this, right? These big crazy names. And sometimes they sound a little scary, like maybe I should not eat this ethyl, methyl, cyclo, whatever thing there. But I think it's worth keeping in mind that this is just the systematic way to name these molecules. And whether it is a dangerous poison or whether it is a helpful medication or something completely benign that just does nothing, that comes out of a lettuce leaf or something, I don't know. This is just the way that you name these things. So there's no reason to be afraid of names like this. Doesn't mean that they're good, but just having a big name does not make something dangerous. All right, so the other part of this thing that we'll see in some names are the halogens. So you can have structures like this. Halogen molecules or atoms, fluorine, chlorine, bromine, or iodine, are really common in organic molecules. They increase the functionality of the molecule, allow you to do reactions with them, allow you to start building things up. Sometimes they completely change the chemical nature of the compound, but they're very easy to name. So the way that we do this is each halogen substituent just takes its name, but instead of going with a YL, like the methyl or ethyl, you just put an O. So this becomes fluoro, CL becomes chloro, Br becomes bromo, and I becomes iodo. So we can name these just the same as all the other rules, just the same as all the other compounds with the same kinds of rules, but we use these names. So how would you name this compound then? Well, same rules. What's the longest chain?
4.
4, which makes it what? Butane. And what's the substituent? 2. Right. So this is going to be 2 bromobutane.
Oh, can I ask you a question? Aren't the halogen gases the ones that? Yes, halogen.
So by themselves, like bromine by itself is Br2 and is a liquid with brown smoke coming off of it. But it also, as an atom, can be attached to other stuff also and do other things. In this case, it has a covalent bond. It's sharing electrons with that carbon in this particular structure.
What is chloroform if it's not really like?
Chloroform, yeah, that's one of these old names. So these compounds, remember, or these names were set up so that we didn't have to just remember all these different random names for different molecules. So chloroform, it's actually, let's do that one. That's a good example. Chloroform is CHCl3, which is a carbon with a hydrogen and 3 chlorines. Common organic solvent. We don't use it quite as much anymore because we know it's a carcinogen, but used to be used a lot more. But how would we name this properly now that we know our rules? Yeah, so it's how big is the chain? Only carbon counts as the chain, remember. So how big is the chain? Just 1. So what is that? Methane. So our whole chain is just this carbon because the main chain is just the carbon chain. The chlorines don't count. So then we've got 3 chloro substituents. So we would call this trichloromethane. Well, you should be able to do that. You should be able to name that.
I have a question. So then is that the formal actual, I guess?
Yeah, so that would be called the IUPAC, or IUPAC is the organization that set up these rules.
Yeah.
That would be the IUPAC name, and the common name is chloroform. And there are lots and lots of molecules like this that have been around for a long time and were named after whatever, and then later, were named before the systematic naming system, and then those names kind of stick because we keep using that stuff. There's a lot of that. So if you go into organic chemistry, you end up taking organic chemistry, you'll have to learn a lot of common names as well, just because it's stuff that keeps getting used, like acetone, all these kinds of common things.
They don't make it in organic chemistry, do they?
They don't what?
Make chloroform.
We don't make it, but we'll use it. We've got like bottles of it. Yeah.
What are you using it for?
A solvent to dissolve things and do reactions.
You're failing.
Right, not to asphyxiate people so they pass out. Right. You can use ether for that too. Use a lot of ether. That's
Oh, either, really.
yeah. Let's take notes here. I should stop talking. All right.
Maybe.
So let's try a couple more to finish this up before we go into anything new. And then on Monday we'll get into drawing structures and we'll add double bonds to all the fun.
We have one more chapter. What?
We don't. We're going to stop at the end of this one.
It's there.
That extra chapter listed on the schedule is like if there's time, so which there isn't. All right, let's try some here.
Yep, we're done.
Good job. Okay, there's your first one. And here's the second one. Second one's a name, and you draw the structure. So you got about 3 minutes. Go ahead. Yeah. An octane means 8. All right, we're almost out of time. So let's look at these. What'd you get named for this first one?
1, 2, 4.
Close.
1, 2, 4, cyclopentane.
Right. So if so this has got to be 1,2-difluorocyclopentane. Because the fluorines are on carbon 1 and 2, whichever
So
way
you
you
don't
start
have
counting.
Oh, you can start there, you don't have to start at the one next to it?
Right.
You start
You start right on there. And then 2,2,3,3 tetramethyl octane. It's going to look like this. So there's our 2 and 3 with methyl groups. Something like that, right? 1, 2, 3, 4, 5, 6, 7, 8. No cyclo there, so it's not a circle. If it's got the cyclo, it's a circle. If not, it's not. Yeah? Sound good? Okay, work on this stuff. Oh, those of you doing the online homework, if you want to do this chapter in the online homework, I can set it up for you. It's a little annoying because you have to draw the structures in their little program.
And if you miss one thing, it's all wrong.
So if you don't want to mess with it, I won't. Or maybe I'll put it up as like practice so you can go through it if you
Yeah,
want.
you can
but-
just practice.
How about if I'm still working on some of the homework, do I still get credit for that or
Yeah.
no?